Okay, today I'm not going to distribute any notes. So you're gonna need a piece of paper in front of you because I will ask something towards the end of the hour. So each of you please have a piece of paper. Okay, can I have your attention please? I still don't have the microphone, so you need to be silent, otherwise my voice is going to be gone. You have never seen it gone yet. It's so ugly. You don't want to hear that. Okay. Were you able to go and were you able to read the comments on the exam? How many of you did read the comments on the exam? Okay, that's pretty good. Now, in those comments, I have a lot of statistical evaluation, like minimum, maximum, and the distribution of grades, which is going to give you an understanding of in which question what you did well or how you didn't do, or the reasons that you failed, and so on and so forth. I think those comments that we prepare for each quiz and for each homework and for each exam are extremely important. There are a number of other things that I didn't mention in class, which I buried in those comments. So those are like class notes as well. If you come to think of it, there are a number of things that you should be able to understand in those comments. So please, before the exam, read those comments carefully, and you're going to see that it will be useful when you come out of the exam. Okay. Now, next week, we're going to have the second exam. The exam will be at the same time as we meet today. We're going to have two classrooms, this one and the one upstairs, V3. And next week, we are not going to have any other lectures. So you're going to have a free week with respect to IE-102 after the exam. And we're going to meet the week after that, which is, it's the 23rd of April. We're going to meet on the 24th and 25th of April, okay, in the sections. You already have your schedule, so you know this information. Any questions that you want to ask me about the comments or anything else about the course? Okay. Today I'm going to talk about queuing theory, which is a very sort of difficult name to follow, but basically it is the theory of waiting lines. Waiting lines are everywhere in our daily life. We wait and we hate. We don't like waiting. Nobody likes waiting. The only good part about waiting is that you can socialize while waiting. Okay? That's the only good part. But on the other hand, if you are waiting with somebody that you don't want to talk to, it becomes even more dreadful. So why do we have these waiting? Is it that important for us as industrial engineers to analyze them? So what we're going to do is we're going to build up some basic elements of waiting line theory in this classroom. And we're going to hopefully continue tomorrow. So this is going to be what we're going to do this week. OK, now first of all, where is this queuing, the word queue, comes from? It's actually British English, but you can simply say that it's waiting line theory. Okay, the E here, usually in English, you would expect this E to be gone, but it doesn't go for one reason or another. Although I started to see some texts where they drop that E. But in the original text, that E is always there. Now, what is very specific about this queuing theory is that waiting lines are everywhere. So there are many examples that one can give to waiting lines. Some of them are more physical. Physical in the sense that you go to the bank and wait there. Now, the waiting structure in the bank has become very civilized. Now, we pick up a number and we look at the numerator to pick our number so that we will be served. Okay, so you don't know how many people are in front of you. You think that some people are in front of you, but they are not. Or sometimes you think that there is nobody in front of you, but it turns out that there are a lot of people waiting in the other lounge. So this is basically one thing. This is physical waiting that you have in a place where you will physically get some kind of a service. Now, another one is the ATM, the automatic transaction machine, where you actually know the people who are waiting in front of you. You don't pick up a number, you simply go into a certain line. And then, but again, the idea is the same. This single server is waiting in front of you, and you are going to be served eventually. Again, you wait there physically, and you usually stand up. Okay, now another one is cafeteria, where the service that you get is a little bit more complex, because you may want to select some dishes, or you may want to only eat a dessert. But basically, again, you wait in that line to pay the cashier, and you go out. Now, traffic is another example. In the traffic, you can consider pedestrians waiting to cross a certain red line. Red light, okay? Not red line, but red light. In other words, you wait there, you wait for the green, and then you pass. That's also waiting. But you don't need to accumulate in a certain order. Almost everybody can pass simultaneously. Whereas in the cafeteria, when you are paying your money, you pay your money for yourself only. In other words, you don't see 6 people together paying their money simultaneously. Although some of the cashiers are very quick and they can handle 1, 2, 3 people at the same time. But in the traffic, on the other hand, it is a little bit different because everybody passes at the same time. So there is some kind of a simultaneous serving being done to those pedestrians. Now, the same traffic example, this time we can talk about automobiles. Automobiles wait in front of certain line, and when they see the green light, well, or the red light, of course, in Turkey, and they are going to pass. Okay? But the idea is that, again, they don't pass one by one, depending on the road, of course. Sometimes they pass all together, so there is some kind of a simultaneous movement. Now, of course, you can conceptualize this as having one server for every lane. If there are 4 lanes, it means that 4 of them can work at the same time. Okay? In the cafeteria, you might have more than 1 cashier to pay your money. So you may go into different lines and pay separately for different cashiers. So you can see that it might be quite complex to understand what's going on, the structure. And one may think why physically we have that kind of a structure. Now, of course, I am going to give other examples where we have, for example, in the telephone, let's say that you want to learn something using your mobile phone. Now, in that case, the queue the waiting line that you go into is a virtual waiting line. There is no real waiting line of that sort. But what you do is you wait. Now, I don't know whether you have encountered some of the service providers will simply tell you that you are 9th customer waiting on the telephone call. Now, some of them are simply playing that lousy music over and over again, which kills you, actually. So it is maybe worse than physically waiting somewhere, because you have to make sure that you hear what's going on there, and then you hear that lousy music, you cannot do anything else, you're stuck. So in all of these examples, the person who is waiting is suffering. So you don't want that person to wait. Now, on the other hand, think about a certain traffic problem. Now, in the traffic problem, of course, the people who are responsible from the flow of the traffic, let's say the governor of Ankara, Ankara Valiliği, are trying to make sure that people will go and will not wait a lot in the traffic. It's also their intention not to make people wait for a long, long time. So, but the problem is, how are you going to solve this type of a problem, even if both sides both of the problem owners want it to be solved. Now, in the traffic example, of course, physical facilities become very important. In the telephone example, on the other hand, cost becomes a factor. So depending on how much the problem owner is trying to pay, you either wait for 25 minutes or 3 minutes. Or you might have some priorities. They have created different ways of dealing with that problem. So for example, they assume that the time that you wait is less important than the time that I wait. So they give me priority. Okay? On the other hand, I am old, so I don't care actually. I have a lot of time to spend. Okay? So I can wait forever. Okay? Whereas you are young and you want to do certain things, may not be very fruitful or productive, but you don't want to stay there. Okay? So actually, these are the things that are used in order to manage these type of lines. Now, of course, in all these examples, we have humans involved. But queuing systems are not necessarily only made up of humans. Now, in the ATM example, which is a good example, where you have humans, you are only interacting with a machine. Okay? Now, there are a number of queuing systems where both what is waiting and who is serving that person, that entity which is waiting, are not humans. A good example is think about a certain mail carrier. Let's say PTT, the Turkish PTT, Posta, Telephone, Telegraph. Okay, so it is mail, telephone, telegraph. Do you know what telegraph is? Okay, have you ever had one telegram coming to you in your life? Okay, yeah, that's what I thought. Okay, so for example, think about PTT. Okay, now what you have is you have mails accumulated in some centers waiting to be processed. Now, those letters are not processed by humans, but they are automatically processed according to the zip code. So there are barcode readers. There are a number of different types of readers once they are classified, of course. They are first classified and grouped. And then after that point, you don't have any human interaction. So what will happen is that you're going to have bunches of letters waiting there. And then a machine is going to pick them up and put it in the correct box so that it will be sent. Okay? Well, not in every center we have that, of course. But this is basically, again, waiting. This time, you are not going to have letters puffing and puffing because they are waiting there. They don't understand, they are dumbs. Okay? And at the same time, you don't have a server who would ask you permission to go to the restroom. So these are more consistent servers and more consistent clients. But still you have this queuing problem because basically you don't know how many letters are going to accumulate in the box that you are going to use. That day you might have a huge accumulation. Next day you might have a small accumulation. So the total time that it waits is going to be, of course, a function of the number that waits there. Okay, so you can see that we don't need to have examples where only humans are involved, but we have examples from systems which are automated all the way. Now, if you think about the systems that, for example, one of the projects that's going on in the 4th year is about a warehouse. I think I had one of the examples in the quizzes was about a warehouse. A warehouse is a place where you place everything. Okay? Now, the warehouse is automated. So everything is done by robots and other machinery, other equipment. So the parts go in, then they are placed in certain shelves. And when the demand comes, they are taken out and put in another shelves. There are a lot of conveyors all around. It's a queuing system, actually. Comes and goes and everything. But you don't have any humans in any human involvement. Of course, again, the objective is similar. We want to minimize waiting if possible. Okay, so this is basically what we are going to talk about. Now, when we have humans, of course, we have the so-called annoyance problem. Annoyance means that you are annoyed because basically you are waiting in an uncomfortable environment, either with a phone or with some people that you don't like to be with, and other reasons. It's called annoyance. So in some systems, you may not have that factor, but annoyance specifically makes these type of systems very difficult to handle. Okay, because you don't know how to put it in some numbers, the effect of annoyance, which is going to depend on the individuals. Now, of course, reason for waiting. Now, why you can say the following. Why do we have waiting at all? Can't we have a world where there will be no waiting? Okay, this might be a good question to ask, but unfortunately our resources are limited. So when you have resources limited, think about the cafeteria example. I mean, at some point in time, if you can have infinite number of kitchens, not infinite, but like, let's say 3,000 kitchens in parallel, if you go to one of them, you are not going to wait, of course. But then going to that specific location is going to be hard. Think about having 300 buildings of the same sort, one after the other. They are all cafeteria. Now, you know that if you can catch the correct one, you are not going to wait. Let's say that we have signs showing you the one that doesn't have anybody waiting, but still going there will be difficult. So there are some physical constraints and monetary constraints that makes us wait for a certain purpose. Similar thing is true for the traffic. Okay? You cannot make roads everywhere. Eventually, at some points, you're going to wait for something. Either it will be with your car, or you're going to wait in the public transport, or you're going to walk, which is another type of waiting in a way, but it's for some people it is more relaxing. But that's, again, you're going to do the same thing in a longer time. It's sort of waiting. Okay, so the reason for waiting means that you are not going to be able to eliminate that. The number of lines in the cafeteria, number of lanes in a road, number of cashiers at the top of the Bosphorus Bridge. Okay, it's limited. I mean, the space is limited. Okay, they are all going to be limited, and at some point in time, you will have a problem. Now, of course, if at this point in time, if we all go to cafeteria, our waiting will be very little. Okay, because there won't be any other people other than us. Okay, the cafeteria will be serving for us. The problem is only if you go at 12:20. Okay, you have a huge problem there. So you can see that economically, talking about these systems and having more lines is not really viable, meaningful in the long run. Because the system is sitting down idle for the whole day. It's only working 3 hours a day. Now, how many parallel cashiers can you create there? There is a certain limit that you can make. And you know that most of the time, there is very little waiting. However, if you are the person to wait in that limited hour that you have in between two courses, you are going to be annoyed. You will not like it, of course. And that's the typical problem that we have with these type of systems. Mostly, the system will be available, but there will be some periods in the daytime where it will be extremely full. But if you look at averages and so on, it will look very nice. Okay, so this is the main problem. Okay, any questions up to this point? Okay, now let me give some examples, and let's think about some examples. Now, this is basically the barbershop example. So I am a very traditional person when it comes to barbers or living style and so on. Well, maybe I'm very traditional in total, I don't know. But I always go to the barber shop, which is sort of in between two districts, the little barber shop that I used to go when I was 6 years old. I shouldn't say I still go there, but I go to the one that I less frequently went when I was a kid. The owner is the same, at least. So what happens is that the number of chairs that you have in a barber shop, or the number of barbers that you have, limits the speed of the haircut or whatever you are going to do there enormously. So let's assume that we have a single traditional barber, and then you have customers. Now, my experience tells me that regardless of what you do in a barber, this is, of course, usually I'm talking about for male. The female barbers, or you can give different names. Actually, we have different names for male barbers as well, are going to have different processes there. But the male barber is very simple. You have like a few things. Well, at least the ones that I go. OK. So it takes 1.5 hours on the average to finish whatever I ask them to finish. So I am going to write it takes 1.5 hours on the average to serve a customer. Now, this is peculiar, actually, because if you ask a lot of things, they are still going to finish your job in half an hour. If you ask very little, they are going to talk a lot, and still we're going to finish somewhere around half an hour. Okay, this is my experience. I always stay there half an hour, regardless of the time that I wait, of course. Okay, it's because I remember a few times telling him that, like, I mean, I need to be a little bit faster, so just cut, and I'm not going to ask for any washing and so on. He says, of course, and then he slows down, actually. So it's still half an hour. Okay, now, this is a small barber shop, so we have 3 customers on the average. Coming in 2 hours. So this is a small district or street barber shop. Okay, so we have, again, this is what we have. So now you can see what will happen. Now, so this means that in a given hour, you can serve 2 customers. The barber has the capacity to serve 2 customers. And because he takes off during your work, actually goes to the restroom, drinks a cup of tea, and so on, and then comes back. So half an hour includes all those vacation times, we call it. Okay? And then the number of customers that arrive in a given hour is on the average 1.5. So 1.5, or in 2 hours, 3 customers come. So how long do you think the barber is going to wait on the average every 2 hours? Every 2 hours, okay, let's draw the timeline. So I am just showing you the averages. So let's say that this is 0, 1, and 2. So I have 3 customers coming in. So let's say that 1 customer is there. And let's say that I have another customer coming here and here. Okay, so it will take half an hour to deal with this customer on the average, another half an hour to deal with this customer, another half an hour to deal with this customer. This is average. Okay, now question is, what is the total time that the barber is idle in these 2 hours? Of course, on the average. I heard it, it's correct. Half an hour. So let's say 1.5 hours or 30 minutes. Am I right? So this is going to be his average. So it looks a good job, actually. You work for an hour and a half, which includes tea breaks, restroom, and then you don't have anything to do for 30 minutes. But it doesn't work that way, unfortunately, because in reality, what can happen might be various. And this is what happens in usual. So you have one customer coming in 9 o'clock in the morning, or let's say 8:30, asking for some kind of a service. And then you have another one coming in, because people would like to go to the barbers before the day starts. So you have a group of people coming in. Now, of course, when you take the daily average, it will be 3 in 2 hours. But there will be a huge accumulation early in the morning, and late in the evening, there will be another accumulation. Usually during the daytime, you're not going to have a lot of customers. So what does this mean? First of all, this means that when you have customers coming here, okay, you are going to have a lot of waiting. The waiting is not only a function of the time that it takes for the barber to serve you, but you have to make sure that the service of the previous customers are complete before you come, or before you start. So for example, if you are the third here, you came at time 0, and you are the third, you need to wait at least 1 hour before the barber can start shaving you or cutting your hair. So you have waiting. Now for the barber, on the other hand, the barber is going to work for 2 hours continuously here, and then maybe another hour in the daytime, and then another 2 hours in the evening. But his average of having 30 minutes off every 2 hours is still going to hold at the end of the day. Now for the barber, you don't have waiting, because he will be working continuously and then resting and then working. But when you look at 8 hours a day, he's going to have 2 hours off somewhere during the day. And most likely it will be not in the early in the morning, not in the evening, but in the time in between. Okay, now, so this is actually what we are going to analyze. So how are we going to analyze this kind of a problem? So this is actually our issue. Now, first of all, how can one analyze a problem like this? Now, let us see what do we have in this problem, okay? Because that's the key to see. Now, can we control the way that the customers arrive in the morning? Probably not. Can we suggest the customers not to come in the morning a lot? Well, we're going to lose customers then. Because basically they come in a certain way that we cannot predict. Now, what we do is actually, we are going to use randomness to represent such phenomena in general. And in this specific case, we are going to base our mathematical analysis will be based on randomness that will occur in this system, in the barber. So what are the sources of randomness? So sources of randomness. The first source of randomness is the arrival time. Arrival time of customers. This is the first source of randomness. Now, what do I mean by randomness, by the way? It is basically uncertain. I may give some interpretation, some meaning. I can do a lot of analysis with numbers, but I don't know what it is. I know the range of it, probably, but I don't know what it is. Okay? What exactly the value that it will take. Okay, so this is the arrival time of a customer. I will never know. Now, even some very good customers like me will always go on a Saturday at, let's say, 11 o'clock to the barber. Some weeks, for some reason or another, I cannot go there at that time. So even very predictable customers will have randomness. Okay? So you cannot simply say that come at this time. It's like consider the emergency room in the hospitals. I mean, you never know when you are going to have a heart attack. If you knew the time that you're going to have a heart attack, it would be very nice, actually. Then we wouldn't be talking about heart attacks. Okay? But you don't know. But you know the chances, depending on your age, depending on your family history, depending on your health status. Okay? Well, the medical doctors can give you some possibilities with respect to time. Similar thing is true for the earthquake. We know that there will be some kind of an earthquake, but we don't know exactly the timing. It might take 35 more years to have another large earthquake, or maybe 74 more years. And they have some probabilities assigned to those possibilities. But you don't know. We have an understanding, but we don't know when the next one will be. But if we come back to our poor barber shop, he doesn't know when the customers are going to arrive. Now, another source of uncertainty or randomness is the time that it takes to serve. Now, although my observation coming from myself is that more or less he always takes half an hour with me, okay? Because I think that's the extent that he likes me, okay? He is not going to keep up with me after half an hour. He is bored. And even if I have a lot of work to do, I need a lot of work, he wants to get rid of me in half an hour. But for some regular customers, okay, the time is going to depend on what you ask that specific day. Okay, you can ask for a relaxing massage, even in my barber. Okay, you can ask for that. So it might take 2 hours. Okay, depending on the status of the customer, actually. Okay, so there are many sources of this randomness. So the question is, how are we going to understand how are we going to analyze this system? Now, before going into that, I will give you a very little, well, we're going to do a very little game. We're going to play a game. So what I want you to do is the following. That's the reason of the piece of paper. Okay. Now, the two sides here, each row, so you are 3 here, you are 4, you are 3, you are 3, you are 4. What I want you to do is, not the middle column, okay? These two. So one result, I'm asking for one result from every row here. I want you to toss a coin. You know what tossing a coin is? Okay? Toss a coin, and if it is heads or tails, write down the sequence of the result. Now, if you don't have money, I have 3 little change, so I can give it to you. Now, when it comes to the middle part, in the middle part, I want you to divide into 2, okay? So each of the 2 groups are going to write a sequence as if they have tossed a coin. I want you to write the sequence of heads and tails that you are going to have. So you're going to fake me, and you are really going to do it. So if anybody here wants to fake, please change seats with the middle row. So I want you to seriously flip a coin. Okay? 20 times. 20 times. 20 times and write it down. 20 times, write it down. Lower the noise. Now, excuse me. Now, if you speak like this, they are going to kick me out of the university. Please. Slow down. Okay. First of all, I should congratulate the fakers. Fakers were much quicker than the others. Okay, because they were faking, of course. Okay. Now, what I will do is the following. I'm going to give you some theory now. And during the break, I'm going to analyze your output and show that my theory is correct. There is no magic here, okay? So, but I will do that during the break, unfortunately, because I cannot process that fast. I would usually do this in another way, but this time I decided that you should all be involved in it. So here, the idea is the following. Randomness can be obtained by even with a simple toss of a coin. Because what you know is you know that the outcome will be either tail or a head. And what are the chances? I'm assuming that we don't have any gamblers in this room yet. Okay, you may become one. But the question is, you are fair, and when you are flipping the coin, you are going to make sure that the chances of coming a head and tail will be more or less the same. Because you already know that. But on the other hand, 20 times flipping the same thing is not necessarily means that you're going to have 10 and 10 every time that you do that. So the first thing that we're going to see is that for the people who have flipped the coin in 20 times in a real manner, we're going to see that you're going to have different numbers of heads and tails. But of course, I'm expecting that on the average, if I average everybody out, I will obtain a number which is very close to 10. On the other hand, when you are faking it, you will always be very conscious, because faking it is not something good. You will always have the consciousness, and you will make sure that you have equal number of heads and tails. Okay? So my theory says that the results that I'm going to obtain from the middle part is going to be less variable than what I obtain from the two parts. Now, the reason that I did this is just to check that. So this means that real randomness, to deal with real randomness, human mind is not sufficient, because we are psychologically affected by the result that we expect to get. So we need to make sure that we can create randomness when we are going to use that using some methodology. Actually, you're going to learn this in a course called simulation. Because in simulation, what you're going to do is you will have a certain mathematical model representation. You'll make sure that you evaluate different randomness possibilities in a fair way. And the machine is going to do that for you. But you're going to ask for some specific information from the machine. But we're going to come to that, actually, I think, the week after the next one. We will talk about that kind of an experiment. So my expectation is on the average, the two sides are going to be 10, but there will be a spread around that 10. Whereas here, the average still will be 10, the spread will be smaller. Now, another possibility that we are going to observe looking at these two is when you actually flip a coin, you might have some runs. Runs means the following. Let's say that you have the following sequence. So here, this means that I have a run of two heads. So if it is similar, the outcome is similar, you call it a run. So this is run number 1, HH. This is run number 2, TTT. This is run of tails. And this is run of heads, and so on. Now, when you do it randomly, flipping coin, you're going to observe that you will have some exceptional runs, very long runs. Okay, some of you were telling me that I'm always getting a tail. Okay, whereas the middle part who has faked is not going to have any of those runs. Now, some of you may know this, so would play with me, but probably I am not going to observe any runs. So you will be so conscious that you will place a head in between a long group of tails. You're going to break the run. Whereas the others, if they wrote correctly, of course, we're going to observe some long runs. Okay? Now, why is this important, and what is the relation to what we are going to study will be what we will do after the break. Questions? Okay.